short video, I'll be doing question 6, which is a question based on the chemical equilibrium. So the question is saying, consider the balanced equation below for a hypothetical reaction that takes place in a 2 dm³ container. So the reaction is 2p, which is a gas, plus Q2, which is also a gas, producing 2pq, which is also a gas. Define the term chemical equilibrium. Now, chemical equilibrium, we said it is when the rate of the forward reaction is equal to the rate of reverse reaction. Now, the amount of each of the substance present in the equilibrium mixture at 300 Kelvin is shown below. So these are the number of moles at equilibrium for all your substances. The temperature of the container is now increased to 350 Kelvin. When the new equilibrium is established, it is found that 1.2 mole of P, which is a gas, is present in the container. Is the heat of reaction delta H positive or negative? Then use Le Chatelier's principle to explain your answer to 6.2.1. Okay, so we need now to answer 6.2.1. Okay, before we do that one, let me just remind you about the Le Chatelier's principle when it based to temperature. So if you increase the temperature, an increase in temperature, we know that it always favors the endothermic reaction. Increase in temperature always favors endothermic reaction. So this is the principle that we know. An increase in temperature favors the endothermic reaction, and we know that a decrease in temperature, it will favor the exothermic reaction. Exothermic reaction. So these are the principles that we know. An increase in temperature favors endothermic reaction. A decrease in temperature favors exothermic reaction. So we need to know now which side is endothermic and which side is exothermic. So the question was saying, is the heat of the reaction positive or negative? In other words, is this reaction endothermic or exothermic? So we need to check now which side was favored, which side was increasing. Is the reactants increasing or the products increasing? Then we will know. Now let's read the statement again. The temperature of the container is now increased to 350 Kelvin. When the new equilibrium is established, it is found that 1.2 mole of Pg is present. Now remember, the reaction here was saying this one, which is 2P, was 0.8. This was 0.8 previously, and Q2 was also 0.8 mole, and PQ was 3.2 mole. Then when the temperature was increased, it was found that now P has 1.2. In other words, this one P has increased now in number of moles to 1.2. So that means that the reactant here has increased. Remember, the relationship between the concentration and the number of moles is directly proportional. If you increase the number of moles, that means you are also increasing the concentration. So you can see that the concentration of the reactants here is increasing. So the reactants here were favored. Then if you increase the reactants, that means your products will decrease. So the reactants were favored. So in other words, if the reactants were favored, now which side is the reactant? Let's go back to this now. Let's look at this. So the forward reaction points to your products, but your reverse reaction is pointing to your reactants. And we are saying now it is the reactants that were favored. It is the reactants that increases. So you can see that the reactants increases from 0.8 to 1.2. So the reactants were favored. That means that now it is the reverse reaction that is being favored. So if the reverse reaction was favored, that means that when you increase this temperature, you favors the endothermic reaction. So our reactants in this case were the endothermic reaction. That means the forward reaction now was exothermic reaction. So that means that when you increase this temperature, you favored the exothermic reaction. That means that this now is an exothermic reaction because heat now is taken to the side of the delta H is on the side of the reactants. Otherwise, it is not on the side of the products. If the products were increasing, we were going to say now it is the endothermic. But in this case, the endothermic is the reactants. So it is decreasing in temperature. So this reaction is exothermic. The reaction is exothermic because of delta H is on the negative side, is on the left hand side, which is from the side of the reactants. So we are choosing the delta H is negative. By Le Chatelet's principle, when you explain it, you're going to say now an increase in temperature favors the endothermic reaction. That's number one. Number two, then you said the reverse reaction is endothermic. The reverse reaction is endothermic. Then you can conclude by saying the concentration of the reactants is increasing and the concentration of the products is decreasing. Okay, I didn't want to focus on these two questions. I wanted to focus on the last question, which is 6.2.3. Calculate the equilibrium constant at 350 Kelvin. I wanted to do this 8 marks. The equilibrium constant. So that's the calculation that I will be doing. Okay, so the first thing that we'll be doing is to draw the table now for this reaction. We have 2P, which is a gas, plus Q2, which is a gas, producing 2PQ, which is a gas. So I'll use this table that we call the Rice table. The Rice table. So now that R represents the ratio. You can see that the ratio of P is 2. The ratio of Q is 1. The ratio of PQ is 2. So that is your ratio. This is the initial number of moles. Remember, they gave us the initial number of moles for all our substances. On that table, they said P is 0.8. So this one was 0.8 mole. And then Q2 was also given to be 0.8 mole. And then 2PQ was given to be 3.2 mole. Then they said now the temperature was increased to 350 Kelvin. When the temperature was increased, the number of moles of P at equilibrium was found to be 1.2 mole. So this is what was given on the statement. Then they said now we need to calculate Kc. Okay, the expression for Kc, we said Kc is equal to the concentration of the product, which is this one. The product is PQ squared all over the concentration of the reactants, which is the concentration of P to the power of 2 plus or multiplied by the concentration of Q. Now we need to find the concentration of PQ, the concentration of P, the concentration of Q. So to get those concentration, we'll get those concentration here. We know that C is equals to N over V. C is equals to N over V. C is equals to N over V. So we do know the volume. They said is 2 mole per dm cubed. The volume is 2 mole per dm cubed. The volume is 2 mole per dm cubed. But we need to get the number of moles at equilibrium. These are the number of moles at equilibrium. In other words, it's the number of moles from here. I'm going to substitute here. The number of moles, I'm going to substitute there. So we already have the number of moles for the P is 1.2. They gave us the number of moles here is 1.2. We need to find the number of moles for Q and the number of moles for PQ. So let's do that. So we are going to fill in now all of this. Now the number of moles for P at equilibrium is 1.2. The number of moles was 0.8 initial. So that means that the number of moles that was consumed, C stands for what was consumed, E is what is remaining now at equilibrium. So the number of moles, if it was initial 0.8, now we need to know how much that was consumed in order for us to know how much was at equilibrium. So it's like 0.8 plus what we don't know equals to 1.2. Now remember, in this calculation, because of we are dealing with the exothermic reaction, on the left hand side, in other words, on the side of the reactants, on the left hand side, this is the side of your reactants, and then the right hand side is the side of your products. So on the left hand side, we're going to say plus and plus. Then on the right hand side, we're going to say minus, because of this reaction is exothermic. In other words, in this case, heat is taken off. Otherwise, if this reaction was endothermic, we're going to put a negative here and a negative here and a positive on the other side. So we say now 0.8 plus something that we don't know gave us 1.2. So we need to find out this x. So that means x will be 1.2 minus 0.8. 1.2 minus 0.8 will give you something like 0.4. Yeah, 1.2 minus 0.8 give us 0.4. So we do know now the amount that was consumed is 0.4. 0.8 plus 0.4 will give you 1.2. So after we have calculated now the amount that was consumed, we can actually use now our ratio to find the other two substances. So we only use the ratio on the row of the consumed. So look at the ratio. Now the ratio between P and Q is 2 is to 1. That means Q is half P. So if P is 0.4, that means now Q will be 0.2. Now look at the ratio between P and PQ. The ratio is 2 is to 2. That means they are equal. So if P is 0.4, that means Q is also 0.4. So we only use the ratio to find the other substances for the consumed row. So we find now that 0.8 plus 0.4 is 1.2. Now 0.8 plus 0.2 will give us something like a 1. So it will be a 1 or 1.0 if you like. So this is a 1 for PQ or for Q2. Now 3.2 minus 0.4, if you minus these two, 3.2 minus 0.4, you'll get something like 2.8. So this is the number of moles at equilibrium, number of moles equilibrium, number of moles equilibrium. I'll take this 1, substitute it here. I'll take this 2.8, substitute there. So the concentration now for my P, 1.2 divided by 2, that will give me 0.6 mole per dm cubed. Then the concentration now of Q2, 1 divided by 2, that's 0.5 mole per dm cubed. So the concentration now of PQ, 2.8 divided by 2, that will give me 1.4. So this one is 1.4 mole per dm cubed. Now you have to take now these values and substitute them on our Kc expression. So we'll substitute all of these and then we'll calculate our Kc. So that is the calculation that you wanted to do. So let's substitute now. So Kc now is equal to the concentration of PQ. We said it's 1.4, then you square it. The concentration of P, we said 0.6, then you square it. The concentration of Q2 is 0.5. So when you punch all of this in your calculator, you'll get something like 10.89. 10,89. So that will be the value for your Kc. So that is how we calculated Kc for this exothermic reaction. Yeah, so this is the end of our video. Okay, before I stop the video, now let me ask you a question. What will happen to the Kc if the temperature now is being decreased? If we decrease remember, temperature is the only variable that affects Kc. So if you decrease the temperature, what's going to happen to Kc? Is the Kc going to increase, decrease, or remain the same? Okay, so in order for you to do this, you have to go back now to, remember we said this reaction is exothermic. In other words, the forward reaction is exothermic, the reverse reaction is endothermic. So the products were exothermic, then the reactants were endothermic. Yeah, the products are exothermic, the reactants are endothermic. So remember, the decrease in temperature favors the exothermic. Go back to the statement that we mentioned earlier on. The decrease in temperature always favors the exothermic reaction. So which side is the exothermic reaction? We said now the products are the exothermic reaction. So if you are decreasing the temperature, which side are you favoring now? You are favoring the product. In other words, the product will increase, but the reactants will decrease. So that means that if you are decreasing the temperature, you are increasing the product and decreasing the reactants. So that means that your Kc now will have to increase. Remember, Kc is equal to the products over reactants. So imagine if your products are increasing now, you are increasing the products. If you are increasing the product, let's take two values. Let's say you take the 10 over 5. So you are increasing the products, you are decreasing the reactants. The answer will be 2. So that means this Kc will have to increase. So if you decrease the temperature, you increase the Kc. But if you increase the temperature, you are decreasing the Kc. So it's the inverse of each other. If this reaction was endothermic, heat was taken in, that means that when you increase the temperature, you are actually increasing the Kc. And if you are decreasing the temperature, you are actually decreasing the Kc. But if the reaction is exothermic, it's the opposite of each other. Okay, thank you.